Namaskaram everyone. We have discussed in the previous session data processing instructions. Today we will see the data transfer instructions. We will explore instructions that handles both single and multiple register value transfers. Toward the end, we will touch on ARM's input-output operations, including memory mapped I/O. Let's dive into ARM's data transfer instructions, mainly focusing on registers and memory. These instructions broadly fall into three categories. First, there is the single register load and store, where a value is loaded into or stored from a single register to memory. Then there is the option for multiple register load and store, allowing loading or storing multiple registers consecutively. Additionally, there is a unique instruction for register memory swap operation, facilitating the exchange of values between a register and a memory location in a single step. While primarily used by operating systems for implementing various locks like semaphores, these instructions are not typically needed in regular applications development. So, in the last session, we have seen data processing instructions. That means we are manipulating or whatever is needed inside for the data, we are doing inside the register. So, we have discussed this is a memory. So, we have memory, right? So this is the memory, and then we have registers. So what are registers are also memory unit, but their size is less and they are very fast. So we have multiple registers inside the processor itself. So we have here in the memory there some data is there, some data is there. In the R, we take that data into the register and do the manipulations here in the register. That means for processing a data, first we need to load a register with the that data. We cannot process the data in the memory itself. We have to load any register with that data. So there are two terminologies. So transferring the data from memory into register, we call it loading the register, load. Transferring the data from register into memory, we call it store. We call it storing the register into a memory location. So these are the two terminologies. First is loading the register. Loading the register means we are transferring a data from a memory location to a particular register. Then second thing is storing a register means we are storing the data in a register to a particular memory location. So this is called data transfer instructions, right? If we are processing, see this is if we are processing inside the register itself, whatever arithmetic operation or logical operation we do, that we call data processing instructions. Even transferring between multiple is, if we are transferring data from one register to another, that also comes under the data processing instruction. But if we are transferring the data between register and memory, here memory is there, right? Memory is the size is more, register size is less. So if there is a transfer of data between registers and memory, we call it data transfer instruction, those instructions which does that. Now these transfer, we have three type of instructions. First is single register load and store. Single register means we are transferring data into a single register. See, this is a register R1. We are transferring a single data into this, right? Or vice versa, if we transfer the content of a single register into memory location, we call it single register. While if we are loading the register, loading register means transferring data from memory into register. single register load, or if you are transferring the content of a single register into a memory location, that is single register store. This is one of the type. Second type is, this is the memory, and we are loading consecutive memory locations into multiple registers. So these are three locations, means values in the memory. We have, suppose, three registers here. We are storing values into multiple registers in a single state instruction. See, from here to here, these values we are storing in a single instruction. So obviously, if you are loading multiple registers, we are going to need multiple clock cycles. So this is different from the conventional RISC architecture, where in RISC what we do, all the instructions need to be happened in a single cycle. But in ARM, that is slight deviation from the RISC, is that some instructions can take variable clock cycle. So in multiple register load and store, there can they, because in one clock cycle you cannot load various registers. So obviously you are going to need variable clock cycle. The, so first is single register load and store. Second is multiple register load and store, and the third type is swap operation, means you are swapping the content of a register with a memory location in a single step. We are not going to discuss the third one. It is used in regular. It is not used in regular application, but we are going to see the first and the second one. So first what we need to learn is the indirect register addressing. So ARM data transfer. So there are different type of addressing, right? What ARM uses is register indirect addressing. That means if this is a memory, right? This is a memory, and there are different locations. Values are stored here. Something is here. Suppose 4, then 2, 5. These are values. Now we cannot we cannot take these values directly using its address. You understand, right? So like in a hotel, there are different rooms. All the rooms are addressed with their room number. Like in an array you have seen index number. Similarly, here in a memory, each thing have an address, because suppose if you want to access 5, how will you access? Suppose is if you want to access this 5, how will you access 5? It has some address should be there. So suppose address is 1, this address is 2, this is 3. So you can say, okay, I want the value at address 3. So that's the concept of address. So in various processor, we can directly access something using the address. So suppose this address is 1, just for example, say 1, 2, 3, 4, and so on. But in ARM, we cannot directly access using the address. First, what we have to do, we have to load this address. Suppose if you want to access this content, this data, then the corresponding address need to be loaded into a register. First we load the address into a register, then we can access the data whose address is stored in a register. So that's what in R we use register indirect addressing. We are addressing indirectly using a register. Means that the address is first stored into a register, and then afterwards we are going to access it. So this is the register indirect addressing. so necessitating a register to indicate memory location for loading or storing data. Suppose I want to store data here at a particular memory location X. So that location address need to be first stored into a register, and then we can store at that particular location. It will be very clear if we just see an example here. So we see here, we are here. Then ADRL, what it does, that the memory address of a table. So just suppose in the assembly there is something is there, table. Its memory address is loaded into R1 register. So the memory address of table is stored into R1. Now R1 is a register which is storing the memory address. R1 is storing the memory address. Now here is the address. If you have studied some programming before, it is somewhat similar to pointers. It is similar to somewhat pointer. That pointer stores the address. Similarly, this register, it can be any general purpose register, it is storing the address of that memory address of table. Now these statements LDR and STR. LDR means load register and STR means store register. These are very common instructions in various microprocessors and microcontroller. LDR means load register. So what is LDR is doing? The LDR R0 comma in bracket R1. What is it is doing? The content of R0, sorry, in LDR what is happening, R0 register R0, it is the register R0. This register is loaded with the content which is stored in the memory. LDR load register, the register is loaded with the content which is present inside the memory. But inside the memory where? Because memory is big, so where it is? In the memory at address. Which address? The address which is stored in R1. So in R1 we have stored a address. So we go to this address, whatever address, suppose it is 4. So this data, suppose it is R. So R is going to be stored into R0. This is LDR. Just take a minute and try to understand it. What is LDR? LDR means load register. Means we are loading register. Which one? The first operand R0. We are loading the R0. R0 means we are loading the R0 register. We are loading means we are storing some values into the register. What value? Value from the memory. In memory where memory is big. So at the address, where is that address? The address is stored in R1. So that is LDR. The second thing is STR. STR means we are storing the content of R0 into memory. In memory where we have to see the address, where we have to go to the register R1. In R1 we have stored the address. At that address we are storing the value of R0. So you can see the comments here, you will understand it. LDR R0 comma R1 means we are loading R0, means R0 R0 equal to in the memory at the address R1. R1 means whatever is stored inside the R1, that thing is stored into R0, that we call loading the register. Then second is STR, store register. We are storing the content of R0 into memory at address which is stored into R1 that address. So this is load register and store register. So let us see into detail these things. So single register load and store, one thing it is can be fairly straight, what I have discussed as LDR and STR. Let us discuss this once again. So this is the memory, right? We need to transfer these value into the register. So transferring the value from memory into register is called load. How to load it? First, the corresponding address, whatever the data we have to load, that corresponding address need to be stored in another register. We call it R1, right? Now this contains the address. Now if we write LDR R0, if we write LDR R0 comma R1, what it will does, it will load the register R0. So this is the register R0. It is loaded with this value. How to identify this value? Because at in register R1 the address is stored. In register R1 this address is stored. That's why the address which is stored in R1, the corresponding value is stored into R0. That is LDR. So we understood the LDR. Now STR means the content of R0 is stored into the memory at location. At what location? In the register, certain address is stored at that location. So this is STR. Now, this is the fairly straight method. Then second thing is we can allow a specific offset, like so. Let us see these things again. See, sorry. Now we will assign some register values, so it will be clear. Okay, so first address, suppose it is 00. Next address will be 04. In R, how will you get the next address? By adding 4. Then the next address will be 08. The next address will be 012. 12 means C. Next address will be 10, then 14. Just adding 4. So 0, if we add 4 to 0, we will get 4. Then 8, then 8 4 12. 12 means C. Then add 4 to it, it will be 16. 16 means in hexadecimal 10. Then add 4, we will get 14. So these are the address. At this address, values are written. Here some values are written. Suppose here written A, then B, then C, then D, then E, then F. So these are the values at the corresponding addresses, and we have some registers, right? So this is R1. Now if we want to access this content, suppose if I want to store C into this register, this is R0. If you want to store C into this, what we have to do? We have to store 08 inside R1. First we have to store 08 inside R1, right? Then if I write this instruction LDR R0 comma R1 inside the square brackets, then R1 means the location 08. Is the location 08, what is the value? C. Then C will be stored inside R0. That means R0 will be loaded with that value, that is LDR. Now suppose in R1 I am storing 10. and in R naught I have value 5. This 5 I want to store at location 14. Oh, sorry, at location 10. Here, instead of E, we want to have, instead of instead of E, I want to have 5. So what we have to do, we have to store the address 10. This address is stored into R1, that we have done. Now if I write str R0 comma in bracket R1, so the value of the R0, that is 5, will be stored inside the memory, where we will see the second operand R1. At that R1, the address is stored 10 at that particular address. That means E here E will be raised and 5 will be stored. This is basic method. Second thing, we can do some offset. Means suppose in R1 what is stored? In R1 suppose 04 is stored. Then we say LDR R0 R1 comma 4. It means this is what is a hash? Hash we have seen in the previous session. What does hash mean? Hash is used to show immediate values. Immediate values means constants. So if I write LDR R0 comma R1 hash 4, that means R1, then we provide an offset. So R1 means 04. So where is 04? Here is 04. Then we provide an offset of 4. So R1 plus 4, 04 plus 4, this value. So this value is going to be loaded into R0. So that is offset, means not the address of R1, but a particular offset is provided, means 4. Means you can see the comment here, it will be very clear from the comments. So R not equal to memory R1 plus 4, means in the memory at the location R1 plus 4. R1 means the content inside the R1 plus 4. So in the R, if you add plus 4, you get the next location. So that location is going to be stored in the R0. Similarly, you can use this offset for str also. Str or R0 comma R1 hash 12, means the value, the content of R0 is not going to be stored inside this 04 location. R1 is storing 04, not 04. We add 12, means at the location 10. So the content 5 is going to be stored here. The R0 is going to be stored R1 plus 12. So this is LDR STR with offset. The third thing is auto indexing. Here you see in the register indirect with offset, we are loading and storing the values with an offset, but the value inside the R1 register here, this is not going to be updated, right? In the both, in the register indirect and register indirect with offset, this value, the register R1, which is storing the address, this is not going to be updated, but we can use auto indexing. Suppose if I am storing the data from one register into here, then I want to store the another data into the next location. Obviously you are not going to store the data into the same register always. You want, suppose if you want to uh, transfer the values from suppose memory location 04 to 14, 5 values you are going to transfer to 5 registers. So once you store the value at 04, then you have another the option that okay, now you change the content of R1, then is load, then change again R1, then load, then again change R1, then load. Then we have an automatic option that the value of R1 is automatically increasing. Means once you load, R1 is automatically updated to the next location. So initially R1, what R1 is storing? R1 is storing 04, suppose 04. Then if I store this value into a register, then the R1 content is automatically updated to 08. That's the flexibility provided by auto indexing. So how to write this? The syntax is we have to add an exclamation mark. You can see here an exclamation mark is added. So if I write ldr r naught comma r1 comma hash 4, that means the r1. So this is similar, r1 comma hash 4, this is similar to this register indirect with option, means r1 plus 4, the value at that memory is loaded into r0. Up to this it is similar to here, but one thing more is happening, that r1 value is updated with 4. This 4 is not 4, it is always going to be updated with 4, because in r we get the next memory location after adding 4. Don't confuse, because we have given immediate value, this immediate value is here. R1 is always going to be updated by 4. Then second is str r naught r1 hash 12, then exclamation mark. You see here we are storing the value of r naught into where? Into the memory at the address r1 plus 12. Up to here it is clear, like it is similar to register indirect with offset. We are storing the value of r0 at the address r1 plus 12. What additionally happening is r1 value is going to be updated by 4. R1 equal to r1 plus 4, right? That is auto indexing. So first way is the basic method, second is with offset, third is auto indexing, fourth way is post indexing. You can just notice the difference in the syntax. See here ldr r naught comma inside the bracket this thing, and then exclamation mark here. You can see here. So this is very simple, quite simple. If I write ldr r naught comma in bracket r1, this is same as the first method. What is register indirect? The r naught is loaded at the location r1. When I say at the location r1, you understand that inside the memory where at a particular address, and that particular address is stored inside r1. Whenever this you see this square bracket, you understand that r1 is storing an address. At that address you are storing inside the, at that address you are going into the memory. So at that address you see inside the memory, and that value you are going to store in the r0. That's clear, right? After that you put a comma, and then you give this immediate value here. That immediate value is inside the square bracket here. After the comma you give the immediate value 4. This 4 is not going to affect here. This 4 is for updating the value of r1. First, the load and store will be happening as usual. See here, str r0 comma r1, memory r1 equal to r0. Simple, means r0 value is stored at the location r1. Simple. Simultaneously, what is happening, that r1 is updated by this value, r1 equal to r1 plus 4 and r1 equal to r1 plus 12 here. In the auto indexing, it was always 4, means if we put an exclamation mark, it will be updated by value 4. Why 4? Because in the r, if you add 4, you will get the next location from 00 to 04, 08, 0c, 10, 14, 18 similarly. So in post indexing, what is happening, this immediate value is used to update the r1, right? So this is the fourth way, post indexing. Then the fifth way is, you can in r each instruction is 32-bit word. The word size is 32-bit. What is word means? Word means is so in the, again draw that same memory box. So this is a particular one word. So this is the second word, means the content here is stored, that we call a word. Here this we call a word, means this we can say it's a smallest addressable unit. You can call it a word. So this content, at one location, whatever the content is, it is called a word. So here in the arm, the a word size is 32-bit, but sometimes you do not need to transfer the entire 32-bit word. So what we can do, if you do not need to transfer the entire 32-bit word, you can transfer, means load or store 8 bits. 8-bit means 1 byte, so you can use instruction ldrb and strb, or you can load or store 16 bits. 16 bits means 2 byte, means 16 is a half of 32, means it is half a word. So you can use ldr sh is an indication for half word, b for 8 bits, b for byte, sh for half word. So you can use these instructions. So we have seen single register load and store, and there are various methods offered by ARM architecture. Now we have to see the multiple register load and store, which provides slight deviation from the traditional RISC concept of uniform size instructions. In RISC, we have seen that all the instructions need to be executed in a single cycle, but due to these instructions like these, ARM is a slight deviation, because if you are loading multiple registers, obviously it is not going to be happen in a single cycle. You're going to need multiple cycles. So these are multiple register load and store. So let us understand this. Okay, so first the instructions is ldm ia. LDM means load multiple, I means increment, A means after. Let us understand this thing with patience, one by one. LDM IA means, if I write LDM IA R1, comma R3, comma R5, comma R6, what is going to be happen? LDM means load. Loading means values are going to be transferred from memory into register. When I say load R1, R3, R5, R6, that means R1 is storing the address, right? So you go to that address, and the content at that address is loaded at R3. Then you go to the next location, and that value is stored into R5. You go to the consecutive next location, and that is stored in R6. Let us see it. So here it is. So here suppose the address is 00, then next will be 04, then next will be, yes, 08, then 02, then 10, then 14. Okay, so suppose R1 is a register here, R1, and in R1 we have stored 04. Then there are 3 more registers. We have R3, R5, R6. Now I write LDMIA R1, comma, in curly braces R3, R5, R6. Okay, then R3 is loaded with the value in the memory at location R1. R1 means 04. So in 04 here. suppose A is stored, so A is going to be loaded into R3. So R3 will have A. Then R5 will be loaded with the next consecutive location. How will you get the next consecutive location? By adding 4. So R1 means 4, 0, 4, 0, 4 plus 0, 0, 4 plus 4 is 0, 8. So here, suppose here B is stored, here C is stored, here D is stored. So this B is going to be loaded into R5. Then if I write, then R6, then next consecutive location, all the consecutive locations are going to be added, means, oh sorry, it is going to be loaded. So C is going to be, this C is going to be loaded into R6. So this, it is the meaning of LDMIA. Load multiple, increase after, means after loading first time R3 is loaded with the value inside, value at location R1. At location R1, whatever the value is, it is loaded. Then increase. Then increase means 04 increase to 08. Then inside the second, and inside the second. This we have written R3, R5, R6. Suppose this was in a sequence like R3, R4, R5. Then we can also write like this: R3, sorry, we can write R3 dash R5. We can also write like this. What does this mean? This will mean R3 comma R4 comma R5. That will the meaning of this thing. If I write R3 dash R5, so if you can write like this, or you can write in the discrete way like we have written here. Here R3, R5, R6, R3, R5, R6. So this is the LDMIA. One more thing is there, LDMIB, means load multiple increment before. That means before loading, you increment it. So LDMIB means before loading, you increment it. Means R1 plus 4. In R1, 04 is there. You go plus 4. That means B. This B is going to be stored here. That means R1 plus 4 is going to be stored into R3. The value at R1 plus 8 is going to be stored R5, and the value at R1 plus 12 is going to be stored into R6. So this is the another way, LDMIB. So there are various variations with I and D alongside A and B. So if you just see this example, it will be very clear. If you understand this example, no more, nothing more is needed, because see here memory is there. So for this time, don't think about the values written here. This is a memory, right? This is the memory. In our previous discussion, we are taking the addresses from top to bottom. Here the address is taken from down to top. You can see here the address is is 200, then 204, then again added for 208, then 20C, then 210, then 214, then 218. Means it is written from down to top. It's depends on you how you write. From top to down you write, or down to top you write. Okay. So this is a memory, right? And you have register. You have register R0, and R1, and R4, and one more register R10. Initially in R10 the value 20C is stored. So this is our pointer register. Pointer, there is no such name as pointer register. I'm just using it. Means this is used to store the address. There is no difference in these registers R0, R1, R4, R10. All are similar. We can use any register to store the address. Okay. Then we have LDM. Let us understand the load. LDM XX means LDM. We can write LDM IA or LDM IB or LDM DA or LDM DB. Let's first understand LDM IA. So if I write LDM IA R10, comma R0, comma R1, comma R4. So what will happen? At R10, what is the address store? At R10, 20C is stored. So what is the address 20C? Here. This is the address 20C. So LDMIA means load multiple registers, increment after means after loading you increment. So first you have to load. So the value stored here, whatever the value, suppose here you are storing 7. So this value is going to be loaded into R0. Then you increment 20C plus 4 will be 210. That means the this value is going to be stored into the R1 and you again plus 4. So this value is going to be loaded into R4. So this is LDMIA. Similarly, let's see increment before. Increment before means in the base register what is written 20C. You go to the 20C, this is a C. 203, this is the location 20C. You increment before loading. You increment is 20C plus 4 is 210. This 210 value is going to be stored into the R0. Then this value is going to be stored into R1 and this value is going to be stored into R4. Now we can write LDM DA, load multiple registers, decrement after. Decrement after means first you have to load. Now in the increment we are going like this, means first we are loading R0, then R1, then R4. In decrement we will start from the right side. We will first load R4, then R1, then R0. That means we go to the location R10. So here whatever the content is here, that is going to be stored into the R4. Then we decrement by 4. 20C minus 4, we will get 208. Then this location is going to be stored into R1 and again decrement, and this location is going to be stored into R0. Similarly, decrement before. That means before loading first time, we are decrementing. So R10 is storing 20C, you decrease by 4. So you'll get this. This is going to be stored into R4, then again decrement, then this loaded into R1, then this value, whatever the value it is here, this value is going to be stored into R0. That is multiple addressing, multiple load and store. Similarly, you can understand the STMIA, STMIB, STMDA, STMDB. Now, you might have heard about stack. In multiple architectures we have a stack. It's a stack in which we can store data. Storing the data in stack we call push. Taking data from the stack we call pop. So in many processors we have an inbuilt stack, but we have seen the architecture of ARM. You might have noticed there is no inbuilt stack in ARM, but programmers can implement the stack functionality using the load multiple and load store multiple instructions that we have studied. So using these instructions, we can simulate stack functionalities, right? But there is no inbuilt stack in the ARM. Okay, so let us understand an example of load multiple and store multiple. So what is here? Here we have to copy a block of memory. This is the memory of 128 bytes, 128 bytes memory from here to here. This is not a single memory location. There are here one word, then and then again one word, again one word. So there are 128 bytes which are at a continuous location. We want to copy. So first what we need to see from where we are going to copy and to which location we are going to store. It is, we are not going to copy a single memory. If you are going to copy a single memory, it's very easy. From here to here, it's very easy. From here, just whatever the address is there, you just load into this. Means you will have the particular address. You load into any register, and at that value, the value you store into this. Use one time LDR and one time load instruction and one time store instructions. It will be easy. But what we are going to do, we are going to copy a block of memory, right? We could have used stack in various processors. We have stack for such problems. They use stack, but here we do not have any stack. So we are going to use load multiple and store multiple operations. So we first have to declare, we have to see from where we are going to copy. So this is the starting address here. This is the starting address. This is going to be copied to at that address. This is not a single block. There are multiple locations here. So the first one is going to be stored at the first one here, copied. Then the second one is going to be copied at the R10 plus 4 next location, and this is going to be stored in the next location. So R9 is the starting address of the source, R10 is the starting address of the destination, or and from R9 up till R11 we have to copy. Means here R9 to R11 we are going to copy to here. That is clear what is R9. So R9, R10, R11 are the registers. We are storing the address. R9 is storing the source address, means starting address of the source. R10 is starting address of destination, and R11 means end address of the source. So first we start, we write LDMIA R9. Wait, yes. So LDMIA R9, then exclamation mark R0 to R7. LDM means load multiple. We are loading multiple registers. So what are those multiple registers? R0 to R7. So this convention I have, this rule I have, syntax I have told you. R0 dash R7 means R0, R1, R2, R3, R4, R5, R6, R7. These are 8 register, R0 to R7. Okay, 1 minute. We can also use single register load or store. There are 128 locations. We can load and store one register and copy here. We have to use a loop. The loop will run 128 times. But here we are loading multiple register, 8 registers. We are using 8 registers. So the, if we have to uh, use a loop, but the loop need not to be run 128 times. It will run how many times? 6 times, because 16 into 8, 16 into 8 is 128. So we have to use the So we have very drastically decreased the number of loops required. Earlier we had to use 128 times. The loop will run 128 times. Here the loop will run only the if you divide, how to get that number, divide just 128 by, at one time we are loading 8 register, you will get 16. So from 128 you are getting 16 iteration, means after 16 iteration this copy will be done. So uh, that's the use of the multiple registers load and store. So from 128 you are, from 128 you are taking to the number of iterations to 16. So we write ldmia r9 comma r0 to r7. So at r9, what is the value here, that is going to be loaded into r0. Then the next value is going to be stored into r1, then the next r2, r3, r4, r7, only 8. We do not know from r9 to r11 how many locations are there. The first 8 locations are going to be stored into r0, r1, r2, r3, r4, r5, r6, r7, right? The first 8 from here to here. Actually, if I use pen I cannot see the marker. So suppose here to here it is, from here to here it is 8. These are going to be stored into r0 to r7. Okay, r0 stored the value at the location r9. r9, r11, r10 are storing addresses. So the value at the corresponding address of r9 is stored r0. The next is r1. So the first 8 are stored into r0 to r7 by this. You can see we have used this auto indexing. That's why these things are, the value of r9 is incrementing by each time. After this execution of this command, what will happen, the r9 value has been changed. Now r9 will see something here. The r9 will be pointing to something here, means the previous value plus 8. So this is the this instructions. After this instructions, what will happen, it will load multiple registers r0 to r7 with the values r9 plus r9 plus 4, r9 plus 8. So 8 values are going to be stored into this, and the r9 value have been changed. R9 might be pointing here, right? Now what we are doing, we are, so from here we are storing into r0 to r7, and next we have to store the value from here to here, right? So what we are doing, stmia r10, then auto indexing r0 to r7, right? So these values, the value in these registers are going to be stored into here. Now we have used auto indexing here also, means r0 value is going to be stored at r10, r1 at r10 plus 4, r2 at r10 plus 8. So 8 locations are stored here. With the values, these values going here, then here, right? Then we are comparing, cmpr compare. We will see these comparisons in detail in the next session. Compare r9 comma r11. So we are comparing r9, this thing, with r11. So obviously r9 is not equal to r11. r9 is here, means the previous r9 plus 8. This is the current r9, and r11 is here. In one iteration it is not going to be equal. So the comparison, after comparison we will get that these are not equal. So branch if not equal, This is kind of a branching instructions. We will see in the next sessions. Means if they are not equal, the control goes back against to here. Whatever it here actually loop means some address is stored. These instructions are stored in the instruction memory. Here some address is there, here some address is there, here some address is there, here some address is there. We are going to the address which is written here. So we branch this to here, we jumping to this loop. Then loop will again run and run, means the next 8 will be loaded here and that will be loaded here. After this complete block is loaded, what will happen? Eventually R9 will be equal to R11. When R9 is equal to R11, it will come out. The loop will break. It will come out of the loop. So this is a copy, a block of memory from, we need the source address, we need the end address, and we need the destination address. Okay. Next we will see the memory mapped IO in R. So up to this we have seen that we are taking values from the memory. Now we have to, this is the memory, but we need values. Suppose you are making a certain automatic system, you need to take values from input output devices as well. Input devices, you add some sensors and you want to see the values from there also. So you have integrated some input output devices and you want to, from input devices, what you want to take the values, and to the output devices you want to give them values. So here is your, here is your processor. In processor, registers are there. Earlier what we are doing, we are taking values from the memory, loading, or we are storing into the memory. That was earlier was loading and storing. Now we have input devices and output devices. We want to take values from input devices and we want to store something into output devices. Means suppose this is a speaker, so we want to give some values, accordingly it will give. Here suppose it's a temperature sensor, LM35. So suppose it is a temperature sensor, so it will give some values. That value first it will come to the processor, then only everything can be happen. So one thing is memory and second thing input output devices. So in many processors what is there, we have separate system for memory, separate system, sorry, separate means memory and IO are treated separately. We are treating them as a separate thing. That means the memory have separate address and the IO have separate address. That means this is the memory and this is IO and this is your processor. In the processor register there, they are treated separately, right? There are separate commands for taking the values from input output devices and giving values. They are separate commands, and here they are separate commands that we call IO mapped IO. But in ARM, the both the memory and the IO are treated as same. Means here there is a memory and certain section of the memory is assigned to have IO. So certain section of the memory is assigned to take IO. So for the processor, for your CPU, whether it is your conventional memory or your input output, the entire thing is treated as a single thing. There is a single address bus, there is a single data bus, there is a single control bus. So that is called memory mapped IO. So there is no need for separate instructions. We are going to use the load and store instructions for taking input output. So suppose you are going to take a value from a sensor, you can use the values is there in the your input device, you can use the load command. You can load the command and the value from the input device will come to the processor, or you can use store command to give the output, right? This is the memory mapped IO in ARM. There is a single address bus, there is a single data bus, and there is a single control bus. But in IO mapped IO, these two are treated separately. There is a two address buses, there the two data buses are there for them separately. So this is the memory mapped IO in ARM. So what are the things? First thing, there is no separate instruction. IO port are treated as like the data memory, and data input is done using the LDR instruction, and data output is done with the STR instruction. So that's enough for today. In the next lecture, we will see the control flow instructions. Thank you.